Hey guys, before watching this video, you should have watched the video of me going over the online learning contract. And if you did that, then you can move on to this video. If not, then go back and watch that video. So for this video, I'm just going to recap that where we left off last was talking about the Earth's layers and the rock cycle. And we did the rock cycle lab with the starburst. And now we're kind of building off that in some regard because we're moving into a topic called plate tectonics. And basically what happens on these plates on the Earth to form geological events like earthquakes, volcanoes, etc. I'm going to give you a little quick overview and then show you a quick brain pop, and that's how we'll do this video. So starting off with plate boundaries, this unit on plate tectonics, there are 7 continents that you guys have learned in your history classes. These continents will sit on plates. History class is more so focused on the continents. We're going to focus on the plates and their boundaries and what happens at those boundaries. I'm going to show you a map in a second. So backstory, there was a gentleman named Alfred Wegener, and he developed this theory of continental drift. He saw that plates on Earth were moving, but he didn't really know how it happened. So his theory plus Harry Hess's theory of seafloor spreading was that underwater, there is the crust, the oceanic crust at the bottom of the ocean floor, and magma's pushing up and essentially moving, but not only that, expanding the seafloor, hence the term seafloor spreading. So their 2 theories together from those scientists made the theory of plate tectonics. So on this map, you can see outlines in red. Some plates are way bigger than others. That's because there are major plates and minor plates. You're not going to be expected to memorize this at all, but you are going to be expected to be able, if you were given like a word bank and told like this is A, and it said A is the North American plate, you should be able to tell me it's the North American plate. You'll be fine. But I mean, in general, just kind of, I always tell kids, if you know where North America is, you'll be able to find all the other plates. So the North American plate is essentially pretty much North America. But what we're focusing on in this unit are the boundaries, like where they're outlined to connect with the next plate. So you can see the North American plate is connected to the Pacific plate, and then it's also connected to the Eurasian plate. But things happen along the red area at these boundaries that cause certain events like volcanoes, earthquakes, mountains, etc. We also talked about a topic of convection currents, and these currents will aid in the plates moving. We did mention convection currents a couple units ago, and we talked about the fact that it's like a lava lamp. The magma in the mantle and the asthenosphere will heat up, rise, cool off, and come back down. That movement helps circulate the plates on the lithosphere that sit on the mantle, and they'll move. Now, they're still moving today. If you remember a topic called Pangea, if you've ever heard of it, the Earth was known to be this one big supercontinent. So all these continents on this map were all smushed together. And eventually, over time, over millions and trillions of years, the continents moved to the places they are today. The reason behind that is because they're sitting on these plates, and these plates are moving. What was I going to say? The movement is similar to the growth of a fingernail. You don't really feel your fingernails growing, but you know after a week or 2, it's time to cut them because they have grown. It's the similar speed to that. We don't feel the plates moving. We don't feel this North American plate moving, but we are moving. So that's that. We're going to move into a brain pot, and this will be like a good little intro for the unit. So here we go.
Are you sure this thing is rated for this depth? You bought it from an air mall catalog. Oh, great. Dear Tim and Moby, when I look at a map, it seems like some continents fit together perfectly. Are my eyes playing tricks on me? From Georgia. You're not seeing things, Georgia. Some continents look exactly like puzzle pieces that snap together. Early map makers suspected that they were once all connected. In the early 20th century, a scientist named Alfred Wegener called this supercontinent Pangaea. He thought different chunks of it broke off and slowly moved apart. Over millions of years, they formed the continents we know today. Wegener couldn't explain why Pangaea split up or how. But there was some evidence to support his idea. Fossils from similar plants and animals had been found oceans apart. The age and type of rock layers matched up too. Wegener's theory of continental drift provided an explanation, but his ideas weren't taken seriously until long after he died. In the 1950s, scientists began mapping the Mid-Atlantic Ridge. It's a mountain range running 10,000 miles along the ocean floor. Tests revealed that the farther you got from the ridge, the older the seafloor was. So a geologist named Harry Hess proposed a revolutionary idea. New seafloor was forming at the ridge and spreading outward to make room for more. In other words, the surface of the planet was moving. Hess called this process seafloor spreading. It seemed to indicate that rock was being forced up from inside the planet. Nowadays, we can see this rock formation in action. Wegener had guessed something like this, but he had no way to prove it at the time. As he suspected, there's a lot going on beneath the Earth's surface. Up here, everything seems pretty cool and stable. But miles below our feet, it's a raging inferno. The deeper you go, the hotter it gets. Earth's center, or core, is as scorching as the surface of the sun. All that energy wants to escape like steam inside a boiling kettle. It pushes outward, putting immense pressure on the middle section, the mantle. Standing in its way is the lithosphere, a rigid layer of solid rock. Well, the lithosphere isn't like a smooth shell. It's cracked into pieces, each one a different shape, size, and thickness. We call those pieces plates. Yep, the Mid-Atlantic Ridge is the border between several plates. They're being dragged apart by forces from deep inside the planet. You can think of it like a pot of soup. The Earth's core is the burner, and the mantle is the boiling soup. As the soup near the burner heats up, it becomes less dense and rises. When it gets to the top, it cools off and sinks down toward the heat. In physics, those are called convection currents. A similar process is driving the mantle, and it's taking the plates along for the ride. That movement is called plate tectonics. It's the engine driving the constant transformation of our planet's surface. Plates have been bouncing off each other for eons. The oceans have expanded and contracted. Land masses have smashed into each other and broken apart. The plates move about as fast as your fingernails grow, so we don't see the ground sliding around under our feet, but we do sometimes feel it. Yep, I'm talking about earthquakes. Seismic activity is greatest along plate borders. At convergent boundaries where two plates collide, at divergent boundaries where they pull apart, and at transform boundaries where they slide past each other. At all three boundaries, there's enormous pressure on the Earth's crust. That's the topmost layer of the lithosphere. The pressure can build up for years. The longer it takes to release, the bigger the earthquake. Yep, and plate movement drives volcanic activity too. At divergent boundaries like the Mid-Atlantic Ridge, there's a gap in the lithosphere. So magma, molten rock from the mantle, is constantly pushing up along the boundaries. These are the most volcanically active places on Earth. Volcanoes are also common at boundaries called subduction zones. That's when a dense ocean plate converges with a lighter continental plate. The heavier plate gets pushed below, down into the mantle. Some of it melts, and the magma erupts farther inland. The Ring of Fire is a massive chain of these volcanoes. Dense sedimentary rock making up the Pacific seafloor is subducted, transformed into metamorphic rock through pressure and heat, and then recycled as igneous rock through volcanic eruptions. In other words, plate tectonics drives the rock cycle, the constant process of transformation and renewal of the Earth's crust. It also creates our most prominent geologic features, mountain ranges. That happens when two continental plates converge. Since they're both about the same density, neither one subducts. Instead, it's like a slow-motion car crash. The plates buckle and warp. The land pushes up into jagged peaks. The Himalayas are still growing from a plate collision that began 50 million years ago. Yeah, Alfred Wegener's theory has come a long way in 100 years. He was practically laughed out of the scientific community for his ideas. But today, plate tectonics is the unifying theory that ties together the entire field of geology. What do you mean, out of juice? We're stuck here? Now what? Oh, thank you.